How many of you have heard of primordial soup? Yeah, there's a funny story about primordial soup. Yeah, when I was a postdoc at Indiana University, when my wife and I were leaving, we had a party, and I made some really elaborate Photoshop primordial soup Campbell's labels and made cans out of them. Gave them to everybody, and everybody had a laugh. Except for one guy. He showed up just that week from Korea. Didn't speak very much English at all. And the culture of America was a complete mystery to him. And so we're at this party, and we give him this can of soup. Well, he took it home and he ate it. It was the worst tomato soup we could find, the cheapest bulk tomato soup there ever was. And so from that day on, he went on to do a postdoc on telomerase and so forth. He was always known as, Julian Chen, the man who ate the primordial soup. The notion here is that if you take mixtures of gases similar to how you might have think the early Earth might have looked, and you add energy to it, either in the form of ionizing radiation or electric sparks that mimic lightning, that sort of a thing, and you recycle that through water over and over and over again, over time, you begin to collect some organic material. Most of it comes from cyanide, by the way. And you actually get some pretty interesting compounds. You get amino acids, and you get purines and pyrimidines. Primarily purines, adenine's a big one. You get some sugars, all different kinds. They typically are caramelized by this point. But you can generate most of the organic building blocks for life in this fairly simple, non-biological way. In fact, things like glycine are detectable in interstellar clouds. This isn't just something you do on planets, but these compounds also are generated in trace quantities in space. Let's compare Halley's Comet with Halley. 52% water, 63% water. About 10% carbon, a couple of percent nitrogen, 25% oxygen, and a bunch of water. This is where life comes from. Most of these compounds and the water that exists on Earth is from the influx of comets. And it's no surprise that living things that emerge from that look an awful lot like it. My son got an A++ on a project he did in grade school because they were looking at meteors. There was a meteor at the time, or a comet. So I brought home a bunch of dry ice, and we made a comet. And then he took it to school in a styrofoam box. The teacher thought it was the greatest thing, but of course the students couldn't touch it because it was frostbite. How do you get from a comet to a living thing? Metabolism is the process. And there's this notion that metabolism may have originated. If you needed X and you used it up, which is what you're going to do, right? Then you might take Y and convert it into the X you need to use it up. And maybe that's a direct chemical equilibrium, or maybe it's something you facilitate in some way with an ion or something. But then you use up Y. And so you take Z and you convert it to Y and you convert it to X. This looks like a metabolic pathway, doesn't it? This creates an interesting conundrum. Here we're not talking about any genetic information. We're talking about the evolution of metabolism independently of the evolution of information. And there is this notion that maybe the central information processing part of the cell emerged independently from metabolism, and the two came together later. There's good conceptual reason why that might be the case. It's related to the software, hardware things that computer scientists worry about. So the apparent ocean has some real problems. First of all, you're not going to make a whole ocean of primordial soup, right? Could it have been a tide pool or an evaporation pool? Maybe, but it doesn't seem likely. There are some scenarios where you can really highly concentrate chemicals in a dilute solution. Seafoam is an example of that. And so there's this notion that maybe bubbles or things were a place you could concentrate these things. Activated precursors are unstable. ATP is a great example. Stereochemistry is a real problem in biochemistry. There's too many isomers of everything. Here's a big one. Making any biological macromolecule is done by dehydration, which is unfavored in aqueous solution, right? How do you drive a dehydration reaction in aqueous solution? Kinetically, you're looking at a couple of intermediates and 55 molar water, driving the reaction the opposite direction. So how do you help that? Probably by not doing it in solution. You do it on surfaces. And so there's this notion generated by Günther Wachteshäuser, who's a patent clerk, by the way. And he looked at mineral surfaces, ultimately iron sulfide. And if you look at an iron sulfide surface, and you put it in a dilute solution of organic material, the organics stick right to that surface and are very highly concentrated. Particularly ionic ones, like phospho compounds. A lot of roots have that giant metabolism chart. You've seen that before, right? With the Krebs cycle in the middle and all this stuff below. If you go through that and highlight every phosphate, it's very informative because all of the major central metabolism of cells goes through phosphate reactions. I mean, the first thing you do in glycolysis is phosphorylate it, right? And then it runs through the reaction. The notion here is that maybe that phosphorylation was a way to stick that to the surface of the mineral. On mineral surfaces, these are two-dimensional reactions now. And diffusion still occurs, but in 2 dimensions rather than 3. And the effective concentration of water is very low. Dehydrations are favored on surfaces. Because when you release that water, you get a big entropy benefit, right? Because the water floats away, it can't come back. And so this notion is life may have originated not as a 3-dimensional thing, but as a 2-dimensional thing on surfaces. And then the waste products of this would accumulate lipids and would have surrounded this metabolism going on and ultimately pulled itself away from it. This generates a hypothesis you can test and is being tested. This argues that if you find really, really early forms of life still existing today, they might not be in the form of cells, but they might be bound on one side by a membrane and on the other side by a mineral surface. And these are being looked for. The folks at the University of Regensburg, who isolate a bunch of archaea, have been doing this for a while now. Taking giant fermenters, loading them up with sulfide and hydrogen and stuff, and running them for years with inoculations from deep crust samples and that sort of thing. No luck so far, but that's a good question. Yeah. And so you can imagine the information processing and the metabolism being joined together in this process. That's all very interesting. I doubt that any of it is correct, but it's the best kind of notion that we have so far. All right, so you take your pen now and draw a giant line through your nose.